Hi, everyone. Uh, this is a Fox presentation for an algorithm, classical algorithm for estimating the output probabilities of low depth and geometrically local quantum circuits in quasi-polynomial time. I'm Matt Kudran, and this is joint work with Nolan Coble. Okay. Sorry. So to start out, I will state, or I'll give the problem statement as simply as I can. So the input to the problem is the description of a quantum circuit. It's a classical description of a quantum circuit, which is given by a circuit diagram. So here I've drawn a circuit diagram for a 1D geometrically local quantum circuit that has depth 3. The gray boxes are the gates. So these are 1 and 2 qubit gates, and we consider worst case instances of this problem with arbitrary 1 and 2 qubit gates. All right. So the goal of, so given this input, the goal of our algorithm is to compute the probability that this circuit will output X when it starts with the all zeros initial state, and you apply the circuit and you measure the resulting quantum state in the computational basis. Right, we want to know the probability for any given bit string X that you receive that bit string as the output of that process. And we're estimating that probability, which is shown here in the upper right hand corner. That's the quantum notation for that probability. We want an additive error estimate to within error epsilon. All right, for a given epsilon. So that is the goal of our algorithm. I've drawn the 1D case here, but we're going to consider all the way up actually to the 3D case. So 3D geometrically local constant depth quantum circuits. So here's a picture of the 2D case. So here I've only drawn the gates going horizontally, but they could actually go into the screen as well. The lattice on the top is sort of the lattice structure of qubits. So we have n qubits laid out on a grid, and the gates are allowed to go between nearest neighbors. The arbitrary 2 qubit gates are allowed to go between nearest neighbors on that grid. So we're considering worst case instances of these types of quantum circuits. Okay, so that's the 2D case. As you probably noticed, it actually takes me 3 dimensions to draw it because I'm using 1 dimension to describe the depth of the circuit, which is the number of layers of gates required in the circuit diagram. So it takes 2 dimensions to draw the 1D case, 3 dimensions to draw the 2D case. By the way, don't worry about the coloring scheme here. That will become relevant later. 2 dimensions to draw the 3 dimensions to draw the 2D case. And if I were to describe the 3D case, which is the main focus actually of our results, it would take me 4 dimensions to draw that with the circuit diagram with all the information in there. So I'm going to kind of punt on that task, but you can imagine what a 3D geometrically local quantum circuit would look like. Each layer of such a circuit would be gates on a 3D grid of qubits. All right, so nearest neighbor gates on a 3D grid, and then there might be some number of layers that, equal to the depth. Okay, so these are the types of circuits that we're considering. Yeah, and I mentioned before, we're considering worst case instances of this task. So that is the problem statement. You're given a circuit diagram. You want our classical algorithm needs to output an estimate of this probability that that circuit will output X. Okay, so let me mention just very briefly some motivation for this problem. Why are we interested in this problem? I'll start out with complexity theoretic motivation. We know that this problem gets very hard as epsilon gets small. So when epsilon is 2 to the negative n squared, is exponentially small in the number of qubits. N is the number of qubits. This task is actually known to be sharp p hard. Okay, so epsilon parameterizes the difficulty, and we know that there are very complex tasks hidden somewhere in here when epsilon is small. This also means we can't hope to have an efficient algorithm when epsilon is that small. So that informs our decision to study the case when epsilon is about inverse polynomial in n rather than being exponentially small. And you could then ask, well, is that case relevant to anything? And maybe part of the reason that we're interested in it is that it seems like it could be relevant for quantum algorithms, for studying quantum algorithms in which there is a near-term quantum circuit C that is then composed with classical post-processing. And what you really care about is the output bit or output bits, but on this picture, simple picture, we'll consider output bit, the output bit of that entire composition, right? So these things are actually studied. People who work on near-term quantum algorithms study processes like this. And those are sometimes called hybrid quantum algorithms, or they have other names as well. And there might be many layers of these things, but we're just considering, in fact, you'll see later, a very, very simple case of this. And in fact, I can say the cases that we're considering. Our algorithm actually simulates it will actually compute an estimate of this output bit in the case where C is a geometrically local and constant depth quantum circuit, and the classical post-processing is very, very simple. So it consists of either one AND gate, logical AND gate on all of the output wires, or a logical OR gate on all of the output wires. Or interestingly, it could be the XOR gate, the parity of all of the output wires. Or we can do any subset of the output wires for those as well. Okay, so actually our algorithm can compute these answers, and these expressions, if you're familiar with the notation, these expressions here actually sort of show you how we can express those quantities as instances of this estimating the output probability of this quantum circuit. Along with that, one line along the bottom of the slide, there's we'll highlight a quick without loss of generality reduction that we're going to do. It turns out that estimating the output probability of any bit string X can be reduced to estimating the output probability of the all zeros string for a slightly modified low depth quantum circuit. So we're going to reduce without loss of generality for the rest of the talk. Our notation will just be estimating output probability of the all zero string. Okay. Now, that was the motivation. I'm going to give also a very quick background of this problem, what is already known. And I'm going to step up through the dimensions. So in 1D, in the one-dimensional case, there's a well-known solution to this problem. You can refer to it under the name matrix product state. It's known under that name. It's known under some other names, but there's a polynomial time solution to this problem when the circuit has constant depth. Okay. In 2 dimensions, and matrix product states, I should say, have been known for decades. So this is a solution that's been known for a while. Okay. In 2 dimensions, the problem is harder, and the solution was only found in 2020 by Bravi, Gasset, and Movasag, and it's actually a very novel use of matrix product states, but I wouldn't say that it's just matrix product states. I mean, it's a particular novel use of them tailored to the 2D geometry in a clever way. And so they managed to get an epsilon approximation of this output probability in time that is polynomial in n, the number of qubits, and in 1 over epsilon. I wish I had more time to explain their algorithm because it's pretty cool, but there's not enough time in this presentation. Okay, so now moving to 3D. The interesting thing here, what makes the 3D case interesting, really, in a sense, is that it's unclear how to extend the Bravi, Gasset, Movasag, I'll say BGM from now on, how to extend that approach to the 3D case without going up to exponential or at least sub-exponential time. And they point out in their paper that there is a way to modify that techniques to get a 2 to the n to the 1/3 time algorithm, which is basically exponential in the side length of the cube. N qubits in the cube into the 1/3 qubits on a side. But not better than that, right? And so this naturally leads to the question of whether perhaps because this natural, nice natural succinct algorithm doesn't seem to extend, maybe that means that the 3D case is just drastically, inherently drastically more complex than the 2D case. So this is really maybe the main inspiration for studying this problem. And our main result shows that the answer that's not the case, or at least the 3D case is not any harder than quasi-polynomial time. Okay, so we give a quasi-polynomial time algorithm to solve this problem in the worst case over 3D geometrically local and constant depth quantum circuits, or because we allow quasi-polynomial time, we actually can do polylogarithmic depth quantum circuits as well. I've written a theorem statement here with the additive error being specifically 1 over n to the log n, which is smaller than any inverse polynomial error, so we can beat any inverse polynomial error. We actually, in the full paper, there's a result that can scale with any error, but it was more complicated, so I didn't want to write it out. Okay, so that's the main result of this talk, and without further ado, I'll move directly on to trying to give some overview of the proof. Okay, so the main interesting thing about our result is that we can't extend the BGM result directly, so we have to go back to the drawing board, and we think a lot about the geometric locality of the circuit in terms of light cones, and trying to use the locality of the circuit to perform some kind of divide and conquer computation scheme where you're slicing the circuit. So that's shown here in this picture. This purple thing is a slice, and there are boundaries of the slice where its light cone extends out into the rest of the circuit. But in general, the circuit can create very complicated, potentially very complicated entanglement. So there's a question of how should this division step really work, because the circuit could be entangled across this cut. Okay. So here's the basic intuition that we try to follow, although our proof will actually be much more complicated than this. But the idea is you can if you look at this quantity that describes mathematically describes the output probability, probability of outputting all zeros, say, there's a way to rewrite it, and I won't get into it, but it's on the slide here. There's a way to rewrite it if you know the Schmidt decomposition, which is roughly describes mathematically the entanglement across this purple slice of the cube. If you know the Schmidt decomposition, there's a way to write this expression as a sum of smaller output probabilities of circuits which are each about half the size of the original circuit. So this can sort of look like a divide and conquer problem. The only thing you need, or the things you need to do that, are you need to be able to describe the Schmidt vectors, if you know what that is, you need to be able to express them as geometrically local constant depth quantum circuits themselves applied to the all zero state. It's not clear how to do that. So these are actually the two problems with this approach and why our proof is much more complicated. Okay. I just mentioned the second problem. The first problem is that this approach only worked if most of the Schmidt mass, the mass of entanglement, is concentrated on just a few Schmidt coefficients, meaning the entanglement is somehow not too complicated. I have to cut for time how we resolved this, but it turns out that we can show that in the cases that we care about, the cases where the output probability is high, there must be many slices of the cube where the leading Schmidt coefficient is very large, right? And that's actually how we end up resolving this problem. The second problem is the one I already said. We need to be able to express Schmidt vectors as low-depth geometrically local quantum circuits. Okay, so the first one, we don't have time to cover it, but it's maybe the less interesting one. Problem number two is the more interesting one. We end up doing this with a technique that I'm not sure it's ever been used this way. It's a technique called a block encoding, commonly used in quantum algorithms, but here we're using it as a subroutine of a classical algorithm, and we are using it to express Schmidt vectors as using quantum circuits. Okay, so a priori, it's not clear why there should be a quantum circuit, a low-depth geometrically local quantum circuit for these Schmidt vectors, but we actually construct one using unconventionally using block encodings. All right, so a block encoding is a way that if I have a state, which has been written here on this slide for the last few slides, but it's psi subscript B union F, which is roughly the state produced by applying the purple gates in this picture. We have low depth geometrically local quantum circuit, and we apply all the purple gates, none of the other gates, and then we measure in all zeros on the M wires, but leave the other purple wires unmeasured, or the gold wires on the border of the purple region unmeasured. That's the state psi b union F. What we really care about in the description I just gave is the Schmidt vectors and Schmidt coefficients of that state. Well, it turns out you can write a block encoding for the reduced density matrix of that state. And if you can do that, you can also write a block encoding for the kth power of the reduced density matrix, which will converge to a projector as k gets large, to a projector onto the leading Schmidt vector. And we know the convergence rate because we know that the top Schmidt coefficient is at least 3/4, which means the next highest Schmidt coefficient can be at most 1/4, etc. So we have a way to express projectors onto the top Schmidt coefficients with low depth geometrically local quantum circuits. So we can then express the divide and conquer step and create new instances as subproblems in divide and conquer that are actually referring to Schmidt vectors from the original problem. Okay, so I just explained this slide where, because we can use block encodings to construct these Schmidt vectors as low depth geometrically local quantum circuits, we can begin to do this divide and conquer process. But there's another problem, and this problem is that since we're only capturing the leading Schmidt vector, or the top Schmidt vector, this way, we have this big error term. Like every time we do this, we lose 1/4 of the mass because the top Schmidt coefficient only captures 3/4 of the mass. The way that we, sorry, this is what I just said. So the way that we deal with this problem is that our division step in the divide and conquer algorithm is also quite unusual. Instead of slicing at one slice through the cube at a time and dividing the cube in half and expressing these two new subproblems, the original problem in terms of the two new subproblems, we actually slice the cube at like log n different places every time we do a division step. And we do an inclusion-exclusion process where we consider all possible subsets of the slices, and we have expressions for every possible subset of the slices and negate the expressions in just the right way, according to this theorem, which I'm not going to go into in too much depth. But the main point of it is that we can express the original quantity we care about as some big sum, polynomial-sized sum of new quantities, where each one of these psi's in this new sum is a tensor product about at least one of these cuts, right? And so that is dividing the original problem into subproblems, which are actually tensor product of smaller pieces of the circuit. So that's the key. That's how this division step works. And each one of these phi's in these tensor products are constructed using the block encodings that I described before. So they are themselves low depth geometrically local quantum circuits. Okay, so that's the division step. And so now our recursive algorithm looks actually like this. This is, again, a very complicated slide. You don't need to understand everything on it, but it's just, I've written the return line here, okay? And so our goal is to compute this output probability of all zeros for this circuit. So at each division step, we find log n slices that are heavy, which means the leading Schmidt coefficient is high. And we perform this inclusion-exclusion division step about that slice, okay, which means returning this quantity where each A is actually a shorthand for a recursive call to the same algorithm on a smaller piece. So we're actually recursively calling this same algorithm to estimate zero amplitude of a smaller piece of the circuit. And each B here is actually a call to the BGM algorithm. And that only happens when the pieces have gotten so thin that we can consider them to be, by paying a small overhead, we can deal with them in the same way that the 2D BGM algorithm is dealt with. All right, so our return line is actually a combination of recursive calls and calls to BGM. Right, and so this gives our final algorithm. And I'll just say very briefly, so the runtime analysis, there are logarithmically many recursive steps. Each step step roughly halves the size of the problem instances we're considering. There's a quasi-polynomial additive cost at each step for running BGM, the BGM algorithm on the 2D subproblems to the right accuracy. And so standard recursive analysis of algorithms will give us a quasi-polynomial time runtime bound. And the error analysis is very involved, but it follows roughly by the theorems I described earlier for approximating the top Schmidt vector and for finding heavy slices where the leading Schmidt coefficient is large, and by the inclusion-exclusion theorem. And that's everything. Thanks for your time.